Hello everyone, I'm Bhavna and I will start our presentation on the paper Physics Diffusion, Physics Guided Hourglass Diffusion Model for Diffusion MRI Synthesis presented at MICCAI 2024. This work, authored by Yuhan Zhang and colleagues, tackles critical challenges in diffusion MRI or DMRI, a vital imaging technique for mapping water diffusion in brain tissue to visualize white matter tracts, aiding in neurological diagnosis. Let's start with the motivation. DMRI acquisition is inherently slow and costly due to the need for multiple B values indicating the strength of diffusion weighting and numerous diffusion directions to capture comprehensive data. This results in scan times of 30 to 60 minutes, which can be uncomfortable for patients and expensive for clinics. Traditional methods like CNNs or transformers focuses on predicting specific metrics like neurite or orientation, dispersion, and density imaging, or diffusion kurtosis imaging DKI maps. However, these approaches are limited. They cannot generate raw DMRI data and require task-specific retraining, which reduces their flexibility. Before we dive deeper, here's a quick overview of today's representation. We will begin with some background on DMRI and its challenges. Then we will explore prior approaches and their limitations. Next, we will explain why diffusion models are a superior choice for this task. We will highlight the key challenges in DMRI applications. This will be followed by a walkthrough of the forward process in diffusion models. The core of our method, the Hourglass Diffusion Transformer or HDIT, will be explained in detail. We will discuss how we adapt the conditions using extract features to enhance model performance. After that, we will cover the dataset and pre-processing steps. We will present our quantitative results followed by qualitative evaluation to showcase the outputs visually. Finally, we conclude the future directions and insights from this work. Let's get started. The author's purpose: a novel solution using generative diffusion models to synthesize full raw DMRI data, not just derived maps. This approach aims to accelerate DMRI by enabling undersampling, collecting fewer diffusion directions, and reconstructing high fidelity images. Unlike GANs, which suffer from unstable training and limited diversity, diffusion models provide stable training and high quality outputs. By incorporating physical diffusion laws and anatomical priors, the model ensures that synthesized images preserve fine details of white matter tracts, such as the corpus callosum, which are critical for clinical and research reliability. DMRI's complexity lies in its 4D nature, combining 3D spatial data with the diffusion directions requiring direction-aware synthesis. Accelerating scans through undersampling reduces acquisition time, but the challenge is to accurately fill data gaps while preserving critical structures. This is where the physics guided approach of the physics diffusion model shines. I will now hand it over to Harshita, who will dive into prior approaches and explain why diffusion models are a game changer for this task.
Thank you, Bhavna. I'm Harshita and I'll cover uh, prior approaches to DMRA synthesis and why the author chose diffusion models. So let's get started with prior approaches. We have CNN based methods for parametric maps and GAN based raw DMRI synthesis. Now, starting with CNN based methods for parametric maps. CNN based approaches like those predicting NODDI or DKI maps take limited DMRI inputs and generate specific parametric outputs. While effective for certain tasks, they can't produce raw diffusion images and require retaining retraining for each new metric, making them inflexible. For example, if a new B value or direction is needed, the model must be retrained, which is time consuming and impractical for clinical settings. Next up, we have GAN based or DMRI synthesis. So, GAN based methods attempted raw DMRI synthesis, conditioning images on B value and directions to enable downstream map computation. However, GANs face challenges like unstable training due to their adversarial min-max optimization, often leading to mode collapse or limited diversity in outputs. They also struggle to balance sharpness and anatomical detail. A major limitation was ending up with blurry or inconsistent results while trying to reconstruct the images. So, now I'll explain why diffusion models are a better fit and why the paper chose diffusion models. So, unlike GANs, diffusion models use a likelihood based loss for stable training, avoiding optimization issues. They generate sharper, more anatomically accurate images and are scalable for high resolution synthesis, crucial for DMRI's 4D complexity. They also support flexible conditioning, allowing inputs like B values and diffusion directions to be integrated seamlessly, which is essential for multi-contrast MRI synthesis. So, however, good, there are some challenges in applying diffusion models to uh, DMRI. So, first off is physics informed noise. So, the noise in DMRI follows physical decay laws, not standard noise, requiring a physics informed approach. So, next up, we have structural fidelity. So, preserving fine anatomical structures like small white matter tracts is critical in DMRI, but denoising or interpolation can blur these details. Without anatomical constraints, models risk smoothing out clinically relevant microstructures. So, integrating structural prior helps maintain the integrity of subtle anatomical features. So, lastly, we have continuous conditioning as a challenge in applying diffusion models. So, DMRI requires model to condition on inputs like B value, diffusion directions, B vectors, and slice positions. Uh, Treating these as discrete labels leads to information loss and poor generalization. So, effective models must learn to integrate these continuous variables smoothly during training and inference. So these are the challenges in applying diffusion models to DMRI. So next up, Prakul will explain the physics diffusion model architecture and its physics guided forward process.
I am Prakul and I will give the high level overview of the model architecture of Phi diffusion model. So this slide basically provides us a high level picture of the Phi diffusion architecture and how the pieces fit together. In essence, Phi diffusion is a conditional diffusion model tailored for DMRI. That means we have two phases to consider: the forward diffusion, which is fixed procedure during training that add noise, and the reverse diffusion, which is learned model that remove noise to create an image. Phi diffusion alters both of these phases to incorporate the information we want. So first, in the forward process, instead of usual uh, add noise add Gaussian noise with variable schedule beta t, Phi diffusion uses the physics of the diffusion MRI to guide that noise addition. Specific, Specifically, it uses the apparent diffusion coefficient ADC uh, and the that ADC map atlas denoted by tilde dn. Tilde dn as is basically a map that tells how quickly different parts of an image will decay under diffusion weighting. Higher ADC means faster signal decay. Using this, the forward process applies an amount of signal attenuation and noise that follow the actual diffusion decay formula. So after T noising step, instead of pure random noise, we have a distribution that reflects what an image would look like if it were heavily diffusion weighted plus some randomness. So this addresses the challenge one we mentioned earlier. So and the for reverse process, Phi diffusion uses a backbone network called HDIT, Hourglass diffusion transformer, to step by step predict and remove noise. The network is a hourglass because it has a downsampling path and an upsampling path like a unit, but it's built with transformer block that uses neighborhood attention instead of standard convolution. So, neighborhood attention is basically specialized self-attention mechanism that limits the attention to local neighborhood, making it computationally feasible for high-resolution images. The result is a network that can capture both local and some global context, which is important for image quality but a reasonable compute cost. HTID will take in not just the noisy image at each step but also conditionally inputs. There are multiple conditions that fed into the reverse model, as you can see here. So first one is the b vector and b value, the q space condition. You can see here uh, are encoded into query embedding that conditions the transformer at the each step. This ensures that the model knows which diffusion direction and strength it's currently trying to generate. And the extract atlas, which you can see here, uh, for the corresponding slice is processed by an adapter network, which you can see here, is processed by the adapter network, and those features are added into HDIT layers and HDIT layers. Uh, this gives the model explicit anatom- anatomical context. Basically, here are value measure threads run preserve structure here. So we can also consider the slice index as a condition. This is subtle but ensures that if you generate slice 50 versus slice 60, the model is aware of that and can use the appropriate portion of the atlas. So now we will consider the physics guided noise evolution forward process. So the uh, motivation is basically the standard diffusion model uses a Gaussian noise schedule. This is appropriate for natural images but doesn't reflect diffusion MRI noise and signal pattern. In DMRI, signal intensity decays roughly as SB equal to S naught dot e raised to power minus B dot ADC. and noise is often Gaussian, heteroscedastic, and structure dependent. Phi-diffusion forward process is modified to respect the physics. So, for Phi-diffusion leverages an ADC atlas, an average diffusion coefficient map as a dn. uh, the ideal relationship between baseline and the diffusion weighted signal is Sn equal to S naught e raised to power minus Bn into dn plus में r dn. So they introduce a residual term rdn here to account the imperfections and the noise. So this this RDN component is basically the essentially the noise component that will be learned. So now the let's see the modified diffusion schedule. So in forward diffusion, instead of learning B, alpha bar t arbitrarily, they set alpha bar t equal to phi t e raised to power minus 2bn dn, and rdn equal to under root of 1 minus phi t e raised to power minus 2 bn dn into epsilon naught, where phi t is a scheduling function over the time step t, and its effect is basically the mean signal decay according to e raised to power minus bn dn as t progresses, and the added noise epsilon is scaled by physically derived various term. So its interpretation is basically early diffusion step, add little noise and preserve the structure, especially in low ADC areas. Example, restricted diffusion in white matter, whereas high ADC areas get noisier faster, mimicking how real diffusion image loss signal. By the final step, T by the final step T, SNT is effectively random noise, uh, but one that has been infused with the spatially varying decay properties of the ADC map. The main benefit is the model does not need to learn the basic exponential attenuation from data. It's back into the forward process. This makes learning easier and align reverse process with how real diffusion contrast emerges, improve realism of the synthesized images. Now, for Hourglass diffusion transformer, Vikas will take over. Thank you very much.
Thank you, Prakul. I am Vikas and I will cover HDIT, which details the hourglass diffusion transformer or HDIT, the backbone of the physics diffusion model. This slide basically introduces HDIT architecture, a unit style transformer with encoder decoder symmetry. The encoder has three neighborhood attention blocks for downsampling, a bottleneck with one global self attention block, and a decoder with three NA blocks for upsampling. The process starts with a noisy image XT generated via the forward diffusion process, which HDIT denoises to cover the original image X0. So basically these slides explain neighborhood attention, which is computationally efficient with a complexity of O of n into k compared to a full attention O of n square. This efficiency allows HDIT to handle high resolution DMRI slices while preserving local structures, similar to convolution networks. The flexible receptive field of NA blocks ensures detailed track preservation, critical for DMRI's fine anatomical features. So, this slide covers multi-scale processing and conditioning. Downsampling uses pooling or strided operation, while upsampling employs interpolation or pixel shuffle. So the conditional inputs v vectors, b values, and slice indices are injected via cross attention or feed forward gating using Gigelu for conditional modulation. The extract adapter resonate based model fuses tracked anatomy features at which resolutions level, ensuring the model captures both local and global structures. So this slide explains why a transformer based unit is ideal. Attention mechanism ensure global coherence across distant brain regions, preserving long structures like tracts, while NA blocks focus on long details. During inference, SDIT predict the noise component e theta to literally recover x0 from xt, as shown in the equation. Xt equals to root of uh, alpha t x 0 plus root of 1 minus xt root of alpha t into epsilon. This iterative denoising is what makes the output so precise. Any question on how attention improve DMRI synthesis? Uh, so now uh, Ada Santuria will discuss about the extract condition adaptation. Thank you.
I am Adarsh Santuria. Now I will continue the slides with uh, extract condition adaptation. Thank you Vikas for the amazing presentation. So extract condition adaptation, an anatomical prior. Here our purpose is that we have to ensure that fine white matter tract structures are prevented in synthesized images. DMRI signal differences are subtle. Without anatomical guidance, a model might blur or misplace tracts. The extract atlas provides a ground truth map of tract locations as a prior. Extract allies, pre-computable allies with 42 major white matter tracts bundles derived from greater than 1000 subjects. It essentially is a set of binary or probabilistic maps indicating where each tract runs in a standard brain space for a given subject's image slice, which can be aligned or mapped to atlas space. You can extract the corresponding traps for that slide. Adapter design, inspired by adapter concept from T2I adapter, text to image adapter. This is a separate mini network that conditions the main difference fusion model without altering its weight significantly. The steps are input the 2D slice of extract atlas for the subject. This might be multi-channel, one channel per tract, so 42 channels. Pixels unshuffle. Down the atlas slice by a factor 2 or 4 by rendering pixels into channels. This reduces resolutions and increases the channel dimension, preparing for multi-scale feature extraction. Here we used 168 into h by 2 into WA2 resonate blocks. Three subsequent blocks each consist of a resonate layer followed by a downsampling studied convolutional. This progressively compresses the atlas information to lower spatial sizes while increasing the channel depth, yielding the feature mat at 1 by 2, 1 by 4 and 1 by 8 of original image size. You can call it a resolution, as you can see. Each of these corresponds to HDIT downsamples levels. Feature alignment. The output feature from each resonate plus down stage is aligned with same resolution stage in HDIT and then added into HDIT features map. The paper says the permitted to be consistent for further addition. For example, after first down black, the adapter produces 1 by 2 resolution. These are added to HDIT features after its downsampling. This is repeated for all three stages. Empty slice handling. Not every slice has tract present. Example, near the top of the brain, the atlas might be empty. Feeding on all zero condition could be informative or even problematic. So they implement a process pre-processing. If a slice atlas is empty, they fill it with a combination of other tracks to give it a some signal. Specifically, they sums the map of all tracks that do exist in the volume and use as a pseudo condition for empty slides with normalization. This ensures adapter always has some input, no entirely blank condition. Here you can see the mathematical formula. If ai is equal to 0, then ai normalize and summation aj for all j with aj not equals to 0. uh, Now its effect. The adapter works like a control for stable diffusion. It guides generation using external map. Here it steers the diffusion model to focus on known track regions. The region is that Phy-Diff output maintain clear track structures. Example, a thin corpusculum or quartic or spinal track in the atlas will lead the model to preserve a similar structure in the synthesized image, reducing the risk of it being washed out by noise removal. This significantly improves structural integrity as noted in the quantitative results. Phi-Diff reduces white matter tracks for better than baselines. Predictions now depends on both physics, physics and adapter C adapter. Here you can see the formula of the uh, E of theta x of t is equal to transformer x of t by suffix and plus adapter C adapter. Now we will go to the multi conditions energy. Uh, because this adapter is separate, Phi-Diff can incorporate multiple conditions simultaneously: baseline image, diffusion query, and track priori without interference. The adapter techniques allows adding the track guidance after training the base model. In practice, they might train the diffusion model on physics plus query first, then fine tune or attach the adapter for track guidance. This modular design increases controllability and flexibility. Now, I will request Manik to hand over the slide and explain the training and evolution part of the model. Thank you.
For the lovely presentation. I am Manik Agarwal and I am covering the dataset pre-processing, quantitative and qualitative results. The HCP S1200 dataset with 9 subjects providing high quality DMRI data at B values of 1000, 2000 and 3000 S per millimeter square with 90 direction per shell plus B naught images. Each subject's 110 axial slices are paired with B naught images, DWIs and 42 channel extract mask split into 7 training, 1 validation and 1 test subject to ensure generalization to unseen anatomy. This setup yields around 2,08,000 samples without augmentation. As noted, Phi-Diff uses a DDMP loss function, minimizing the difference between predicted and actual noise. Training occurs in 2 stages. First, the base model is trained with physics and query conditions over 1000 diffusion steps, then frozen to train the extract adapter. Using two RTX 3090 GPUs, training took 40 days with mixed precision and a batch size of 4 per GPU. Adaptations like lower initial resolution and fewer steps ensured feasibility with modest hardware. Phi-Diff achieves state-of-the-art performance with SSIM of 84-88% and PSNR of 23.6 to 25.8 dB across B values, outperforming baselines like UNet, QDL, and latent diffusion. Even at high B values, Phi-Diff maintains SSIM of 81.4% and PSNR of 23.6 dB. This table shows Phi-Diff's consistent superiority, especially in structural preservation. Phi-Diff closely matches ground truth, preserving track details and directional contrast
with slightly noisier outputs reflecting real DMRI texture. Phy-Diff combines physics, transformer-based diffusion, and anatomical priors for robust, high-fidelity synthesis, enabling reduced acquisition times. Future work includes acceleration, inference, extending to 3D modeling, adding pathology-aware conditioning, and applying to tasks like tractography. Thank you.